Sorry I didn't see you there. Well, now that I have your attention, let's discuss Lab 10, Experiment 22. So what we got here is the main guiding concept that like dissolves like. In solubility, if you mix two things together, sometimes they will dissolve together very well, and sometimes they will not dissolve very well at all. Part of that comes down to polar versus non-polar. For example, you know, water is a very good universal solvent. In general, it dissolves a lot of polar things. So in here we're kind of exploring that concept a little bit, specifically with regards to cations and anions together in salts. So let's just say here we have cation C with the charge of plus Y, and we have anion A with the charge of minus X. If you look at this here bad boy, what you see is that we have CXAY. The reason for that, of course, is that you want to make sure the stoichiometry works out here. Okay? So it's going to be the coefficient of 1 is going to be the charge of the opposite, essentially, to make sure it evens out. It'll make more sense when we have a real example and we're not looking at hypotheticals. So as you have this equation here, you have your solid that's then going to dissociate into its component ions. So XCY plus, aqueous, YAX minus, aqueous, from the solid. And our KSP is our solubility product constant, okay? So this is like KEQ, except in this particular equilibrium case, it's a solubility product. So when you break this bad boy down, we've got CY plus to the X, and we have AX minus to the Y, okay? So what we're gonna discuss for this experiment here is calcium hydroxide, okay? So when you break that down from its solid form, we've got apologies everybody. We have 1 calcium ion and 2 hydroxide ions. So in solution, when we got a little beaker there, we got some things floating around. You know, they're interacting, they're chilling. So we're going to have 2 hydroxides floating around for every 1 calcium in that solution. And the way we're going to use that to determine our KSP is in this experiment, for part 1 and 2, we're going to use pH. So the way we do that in the first part is with pH paper. Is there a better word for pH paper? No, pH paper. And then we're going to do that with the pH probes that you guys are very familiar with. You love those things, you've calibrated them, you've used them, you know what they're about. So we have pH, which is always equal to the negative log of the concentration of H+. What we have here is that we're going to know our pH and we're going to need to solve for our unknown of H+. So we break it down, we solve for the unknown, which mathematically gives you 10 to the negative pH. So we plug in our value for whatever we get for pH on 1 and 2, and we're going to get a concentration of H+. Now, do you see H+ in here? You don't? Interesting. So what we're going to have to do is we're going to have to recall that Kw is equal to the concentration of OH minus times the concentration of H+. And when we do that, we're going to be able to plug in 10 to the negative 14 for Kw, which is the value at standard conditions. And our concentration of OH minus is going to come from Kw over the concentration of H+, which is going to be 10 to the negative 14 divided by our concentration of H+, when we solve for our unknown here, which is that OH minus. And as we walk that through, we're now going to have the concentration of OH minus. Is that all you need to solve for KSP? No. No! Okay, edit that. I panicked for a second. Okay, so is that all you need to solve for KSP? Yes and no. Okay, so we're going to plug this bad boy in, right in there. We've got 11, okay? And remember, there's 2 OH minuses for every calcium. So when we do that, we're going to have to plug in a half of this bad boy here. Okay, so if you write it out, what it's going to look like is our KSP expression, or value, is going to look like KSP equals 4 calcium 2 plus 1/2 concentration of OH minus, okay, times concentration of OH minus squared, and that's what you're going to use to solve for KSP. Thanks for being here, everyone.
In the first part of experiment 22, we are using the pH paper to determine the KSP of calcium hydroxide. So I've got my beaker here of calcium hydroxide, and I'm going to use the stir rod to dip into the calcium hydroxide, and then I'm going to dab it on my pH paper here. okay. And so my pH paper is the shade of blue, and then according to this, we have a pH of about 13. Okay. Okay, so in part 2 of experiment number 22, we're using a pH probe, which I went ahead and calibrated to determine the pH of this diluted calcium hydroxide solution. So it's 5 mils of calcium hydroxide and 95 milliliters of water. Okay. Okay, so I'm going to go ahead and put my pH probe down into my solution, and I'm going to hit record. And our pH is right around 10.5.
Hello folks, welcome back to Gen Chem. I'll be your host today. Alright, so the third part of Lab 10, Experiment 22, is as follows, a titration. I know y'all have never titrated anything before in your life. Alright, so again, what we're going to do for this is going to be determining that concentration of OH that we have in solution. So in this case, we're titrating with HCl, which is a strong acid. So when we have OH minus plus HCl, we'll get H2O and Cl minus. And what we're going to do is we're going to use a methyl orange indicator. And this indicator is going to very slightly change from a yellowish color to more of an orange tone when we reach that neutralization point, at that equivalence point, if you will. So, as you can see here, we have one OH minus for every one Cl minus. So we've got a 1-to-1 ratio of OH minus to Cl. And so when we do our C1V1, C2V2, or M1V1, M2V2, whichever denotation your Gen Chem professor or your Lab 2 uses. So we'll have the concentration of OH times the volume of OH equal the concentration of HCl times the volume of HCl at that equivalence point, okay? So now that's the titration portion. That's how we're gonna get that concentration of OH minus. We'll solve for it by dividing out by the volume of OH minus, as y'all have done many, many times. So recall again that this CaOH2 to Ca2 plus is 2OH minus. It's gonna be the equation that we're using here. So in this case, we have that OH minus concentration. Instead of doing that pH equation, we can just now get that COH that we've solved for over here. And when we do that, we'll plug that into the KSP, which is Ka, which is calcium 2 plus times OH minus squared. And so again, this calcium, as you can see, there's one for every 2 OH minus. It's not a 1-to-1 ratio in this case, as we discussed in the previous. So now what you're going to do is you're just going to pop a half in front of the concentration of OH minus. You're going to toss that bad boy in there. Just going to solve it through like that. So you'll have KSP equals 1/2 times OH minus times OH minus squared. And that, my friends, is how you're going to get your KSP on the second try.
Okay, so in part 3 of experiment 22, we're doing titration, imagine that. In our burette, we've got hydrochloric acid, and then in our Erlenmeyer flask down here, we have the calcium hydroxide with methyl orange as the indicator. And my lab partner here is going to go ahead and conduct the titration.
Yeah.
Okay, so as you can see, we've completed our first titration. We've got a nice slight orange color there, and it took approximately 49.2 milliliters. And so we just completed our second titration, and it took approximately 49.7 milliliters to achieve that slight orange color.
All right, hit it.